Okay, so let's go and start from here. So if we have a problem with more than one conversion factor, you may have to do a conversion multiple times, okay? Now when we do conversions multiple times, it's very, very important that you break the problem down and you just handle it one step at a time, okay? Has anybody ever tried to juggle? Yeah. Yes. So the important thing about juggling is actually the same thing. It's to break the steps down so you only have to concentrate on catching one thing at one time. Okay? All the other steps should be in the air transitioning, so you only have to catch this, that, this, that.
Can you juggle?
I used to, but not very well. Like only 4 objects. Yeah.
Oh, only?
I haven't been able to, I haven't tried in like 15 years. No, I'm good. I'm pretty sure that's not like riding a bike. But, so anyways, the important part in chemistry is that situations get very, very complex very quickly, okay? If you try to solve a complex problem, you're going to have a lot of difficulty and probably fail. Humans on average have about a 30% chance of solving complex problems, okay? Like the best political science person predicts election results 30% of the time. The best financial person predicts what the market's going to do 30% of the time. The best baseball players, what are their hitting averages?
In the 300s.
Yeah, 300s. That's like the very top, and that's 30%, right? Yeah, so, if you can simplify problems, simplify them, okay? Take it one step at a time. Now, this right here would be an overall game plan for tackling a problem like this. And so what we have here is, there's my laser pointer. Ooh, that's a lot light. So a doctor was prescribed a dosage of 0.150 milligrams of Synthroid. If you only have 50 mcg, does anybody remember what that is? Micrograms, very good. Tablets in stock. How many tablets are required to provide the prescribed dosage? You may think that, why would I ever care? Actually, this is a problem that almost all of you eventually will have to deal with in some point in your life, okay? Happens incredibly often. So, again, how do you solve any problem? What's the overall structure of that? Okay, I'm going to drop profound knowledge on you. All problems in life that can be solved can be incremented towards solving with these 3 steps, okay? And in fact, every study ever done has said that you'll be 80% more successful if you expressly think about problems in these 3 steps, okay? So, step number 1, where am I, what do I have? Okay? Write it out, express that. So in this problem, I have, let's see, a dosage of 0.150 milligrams. That's my end result that I want to get, right? So that's what I have. I also have 50 microgram tablets, don't I? Okay? And so those are things I have and I know. All right. The next thing you want to write out is, what do I need? Where do I want to be? Okay? Notice I'm trying to make this broad because literally this is like, I want to be a doctor in 10 years. What do I need to do? This is also, I want to solve this trivial problem in chemistry. What do I need to do? Okay, it is like profound knowledge. All right, now, so I need what? I need how many tablets, right? So I need a number of tablets at the end of this, don't I? Okay, and I want to expressly write that out. So I'll write that out. I need some number of tablets. That's my goal, okay? If you want to be a doctor in 10 years, doctor in 10 years. If you want to be the world dictator in 10 years, world dictator in 10 years. Okay? By the way, if you ever want to see somebody that's like an actual fantasy novel come to life, look up the history of Xi Jinping in China. He's really kind of like a crazy character. Like, communist killed his father, and
So what year was this?
he's the current dictator in China.
Right, okay, got it.
Yeah. I said his name slightly wrong. It's actually like Xi Jinping. But yes. I can't get the accents right. My accent is not correct. Anyways, really, really interesting history. Not exactly a role model I would recommend you to live up to, but really cool history. Or maybe he is a role model you want to live up to. I don't know. Most Americans probably would agree not a role model to live up to, but anyways. So the next step, the last step, is writing out a plan of how to get from what I have right now, where I am right now, to where I want to be, the answer I want to get, right? And so in this case, we're going to have to relate what we have to what we finally want. So what we finally want is tablets, right? Well, this one right here has tablets in it, doesn't it? Is there a way we could express that in such a way that would be helpful to us? We could express that in a conversion or equality, right? And so we could say, I have one tablet, and that equals 50 micrograms, right? Okay. Now, we know a little bit about prefixes now and units, right? And so if we have a different prefix, that's just a conversion, isn't it? And so now we have tablets. They are then related to micrograms, right? More importantly, they're related to grams, right? And that means that this number here is now related to that number, isn't it? And so let's see. I should start with 0.150 milligrams, right? And then I'm going to want to use this conversion factor here. It's not quite in the right units though, is it? It's the wrong prefix. Anybody know how those are related? Milligrams, micrograms? Okay. So the easy way to do this, in my opinion, is actually, there's a few different ways you can do this because it's real world, it's math. There's not just one pathway to get from A to B, right? This isn't fake math where we just set things up so there's only one way. It's a real problem, real world, right? Okay, so the easiest way, in my opinion, to do this is I want to get rid of milligrams, right? Okay, I want to get into tablets eventually, meaning I need to get into micrograms first, okay? And so the easy way to do this would be to write out 0.150 milligrams. I'm going to go ahead and do the train track method, which is like that. Everything on the top I'm going to multiply. Everything on the bottom I'm going to divide by. Okay? If I put two things together in a train track, one slot, they should be true. They should be an equality. They should be some sort of relation. Okay? Okay, now I need to get rid of milligrams, and I need to get into micrograms. Can everybody read that okay?
Yeah.
Kinda. Okay. Okay, now these are both related to something, aren't they? They're related to grams. Okay? So personally, I prefer doing it like this. I prefer saying this is 10 to the third or 1,000 of these in a gram, right? And this one here is 10 to the sixth. There's 1,000,000 of those per gram. Okay? And then I just have to cancel out and go like that. Okay? That's one way you can do that. Alternatively, you could do that separately outside of this structure, and you could go, there are 1,000 micrograms for a milligram. Okay? Okay. I personally find it easier just to relate every prefix to their base unit. Then I never make mistakes. I can do this at like 3 in the morning after I've had 2 or 3 days where I have only slept an hour or two, and I never make mistakes. Okay, have I done that? Yeah, I have.
So for like the quiz, we need to remember that like the micro would be 10 to the 6, milligrams would be, like we need to remember
Yep.
all those.
Yes, you need to remember the prefixes.
For all of them.
Yes. But it's much easier than you think because it's a pattern. They're separated by 10 to the 3s. So all you have to remember is the overall structure. It's milligram, then microgram. Milligram has to be 10 to the 3, microgram has to be 10 to the 6th. Then the next one's nano. That one has to be 10 to the 9. See that they go up by 3s? Yeah. So it's easier to remember the pattern. The big ones, by the way, that are going to make them bigger, like kilo, mega, giga, you guys actually see those on computers and in commercials all the time. Like your power bill, if you ever look at the power bill, is kilowatts. Okay? So it's actually kind of interesting. You're always seeing those all around you. You may just not have realized it. But yep, you should go ahead and get those down. If you practice, honestly, just practice problems in themselves are going to help you remember those quite a bit. Okay? All right, so right now I have canceled out milligrams here. And so now I need to use and get into tablets, don't I? And my relationship that I had was 1 tablet, just going to put TAB here. And that is to 50 micrograms. Okay. Again, expressly cancel out units, especially while you're still learning, because that'll keep you from messing up, right? See how once I do the math for this, I'm going to end up in tablets, aren't I? I can double check. I never am unsure. I know I'm going to be right. I just need to plug into my calculator and actually do it, right? Okay. Does anybody have any questions about that so far? Fantastic. You can, by the way, simplify problems if you want. But if you're unsure of how to simplify, use your calculator to just expressly calculate, okay? Okay. Like, for example, I simplified this portion right here, right? Did everybody understand how I could simplify that and why? Okay. Okay. And so that's actually what that looks like when I type it out. In the type out portion, because your book oftentimes does that, where it's going to do the 1,000 micrograms or milligram, they always tend to use the simplified version, which is one of the reasons I showed you the other way. Okay? You do not have to simplify it first. Anyways, so that's the formula. Note, by the way, that these things right here, this is an exact, these are exacts. They don't count for sig figs, okay? When we're trying to figure out the final value, what we're going to do is we're going to plug this in our calculator. So this, divide by this. All right. And then we're going to get a number, and it might be 20 digits long, right? Your whole screen on your calculator, doesn't matter. Okay? It might be 1 digit on your calculator, just a 3, right? But what we're going to do is we'll round it to the correct number of sig figs at the very end. Okay? Not each step of the problem. If you round each step of the problem, you'll end up with errors every time. And you're going to be going, why do I always get like a 5.21 when it should be 5 exact? And you're going to be like, Dr. Clausen, what's going on? And it's usually rounding. If you're just a little off every time, you're rounding. Okay? When you shouldn't be rounding. Anyways, this number right here is then going to come out at the back. In this case, because we're going to be counting up number of tablets, technically speaking, you probably would just be better served by keeping it as a 1 sig fig or an exact number. But theoretically speaking, because of these numbers here, this is actually a measured number. Okay? If you wanted to dose someone exactly, you could split parts of tablets off. Okay? Anybody ever had to cut tablets? Yeah. And you can do it. It's not that hard. It's easier if you have something that splits them in half, and then you just half. But okay, so if you pace on a treadmill, it's 65 minutes per meters per minute. Excuse me. How many minutes will it take you for you to walk a distance of 7.5 kilometers? Okay, so go ahead and get a little bit of a start on me. I'll give you a half a minute or a minute to get ahead of me. Or maybe you can complete the problem. Okay. Everybody making good progress? Don't forget your Plicker card if you haven't already gotten it out, because we'll totally do some Plicker. So this was one of those multi-unit conversions, wasn't it? Where you had to do it in a couple steps. Okay. And so, again, you write out expressly, and especially if you're not exactly sure where to go. What do I have? What do I need? How do I get there, right? Okay. And so I have 7.5 kilometers. I need minutes, don't I? Okay. I've been provided a bit of a pathway to help me get there, which is that meters per minute, right? That number relates length, distance, to time, doesn't it? Okay? And so that's my relation between the two, isn't it? That's a distance, time. Okay, so somehow or another, I need to get from kilometers into meters, don't I? Okay. And is there something I know that should be able to help me get there?
1,000 meters is 1 kilometer.
You got it, yeah. The prefixes. So kilo, if I get paid 10K, I get paid 10,000. And so I'm going to be doing 1,000 meters is 1 kilometer. That's going to be that equality or conversion factor, right? Okay, and so I go ahead and take them. 7.5 kilometers. There's 1,000 meters in a kilometer. Again, expressly cancel things out as you go. It will help you not make mistakes when you're nervous, excited, whatever, tired, whatever's going on. Okay? And again, I'm going to need to get out of meters and go into minutes, right? And I have that conversion factor as given, right there, right here. And so I put the meters on the bottom, I put the minutes on the top, okay? Okay, now that we've done a few problems and stuff, it's 2 sig figs, by the way, because both of these are 2 sig figs, but your least number of sig figs is the one you go with. And so 2 sig figs right there. Okay? That last 0 being a placeholder 0. Okay. Now, one of the things I want to point out here is that most of math in chemistry, because we have to give you certain constants that are going to get used, and those constants have to be expressed with units, there actually isn't a whole lot of need for formulas in chemistry. Okay? I'm going to end up giving them to you because that's what we do. But I personally probably only memorized maybe 5 or 6 formulas my entire chemistry degree. Maybe. You just don't need them. The reason you don't need them is cancel out units. If you cancel the units out, you can always get from anything to anything, right? Yeah. As long as you use things that have to be true, that have to be related, you can do that with anything.
Why would you start with the 7.5 instead of the 65?
You could actually. If you want to, you could start with the 65 meters per minute. That'd be totally fine. The only hard part of that is it's easier to start with something that doesn't have something on the bottom or top. Does that make sense? If you start with the 65 meters per minute, you have to figure out which one you want to end up in. But no, you could very well. If you had 1 and 2, you could have started with that one. And you just would go, I want to be in minutes. So you'd put the 1 minute on top. And then you'd work by canceling off the units from there. That would be totally fine. No problem at all. Like I was mentioning, this is a real world problem. And so there is not just one pathway. There's probably about 4 or 5 pathways just off the top of my head that would be optimized all about the same length. Yeah. So, oh yeah. Yeah, please do. Any other questions at all, or did that take care of that? Okay. Yeah, fantastic. Okay, so let's talk about density here. So this compares the mass of an object to its volume, the mass of a substance divided by its volume. It's defined as what I just said, which is density equals mass of a substance divided by the volume of the substance. Have you all heard of density before? Fantastic. I thought this high school was pretty good. Okay. All right. And so, substances that have higher densities are going to contain particles that are going to be more closely packed together. And that's why they typically have more weight for volume. This is an overall trend, okay? It's not true every time, everywhere. All right. But overall, yes. They have more particles per unit of volume. Lower densities are going to contain particles that are typically further apart. You can actually kind of get this from looking at like plastics versus styrofoams. And so like the plastics that tend to sink don't have a lot of space between them, right? Whereas like the styrofoams have air blown into them and are really puffy, right? And so they tend to float, okay? Metals like gold and lead, they have higher densities. So this is actually a place where this is what your book says, because their atoms are packed closely together. That's not actually totally true. What's really true is that their specific atoms actually weigh more. Okay? So even if they have the same spacing as like wood, they weigh more. Okay? So they end up with higher density, right? This right here is sort of the most common use of density. Specifically, this would be the specific density or the specific weight of these objects. Essentially, it's the density versus water. Okay? Things that are less dense tend to float above things that are more dense. So, for example, if you have water, you put a wood in it and it floats. That means it's less dense than the water overall, assuming you didn't do anything special with the shape. Okay? If you were to then put something and it sinks, that would typically mean it's more dense than the water, right? The same thing actually holds true for gases, by the way. That's why, for example, if you put helium or hydrogen in a balloon, it floats, right? If you blow it with the air from your lungs, what does it do? It does not float. Yes. It plops down on the ground, right? And that's because you added the balloon's weight to that, and therefore it's more dense than the surrounding air. Okay? Okay. Anyways, this is an example of that. It has the densities here. I will warn you that in this class, because there are more complexity to the world than we can present in one semester, we do tend to take liberties with specific terminology, okay? If you want to really, really get into the weeds, you got to go for a degree or something. Or you can independently go into the weeds, okay? Yeah. So anyways, these are some different solids, liquids, and gases and their densities. And right here you can actually see, like, you go to the gas pump, you see that shiny surface on top of the water puddles. What's the shiny surface? Gasoline. Yeah, the gasoline floats on top of the surface of the water. Okay? And that's what you're actually seeing. Anybody have any questions about that so far? No? Fantastic. By the way, if you want to make something float, what's an easy way to do that? If you want yourself to float in water, what do? Yes, you fill up your lungs, right? Because the air and gases in general are less dense than water. And so when you breathe in the air, it lowers your density, doesn't it? Because you increase your volume. Yeah. If I took my water bottle, wherever the hell I put it, probably over there somewhere, and I were to empty it and it was a water ball of air, what would happen if I threw it in water? Float. What if I scrunched it down then capped it? Yeah, it might sink, right? Because I took away a bunch of the volume. Okay? Okay, so let's talk about conditions and health that is concerned with this. So a condition of severe thinning of the bone is osteoporosis. This may occur. Scanning electron micrograms, or SEMs, actually show a normal bone. And then this is bone with osteoporosis. And this is quite literally a loss of bone minerals and a loss of density of the bones. Okay? And it makes them much weaker, much more prone to fracture. Right? It typically happens when people age. And there is things you can do long term to help osteoporosis, assuming you don't have any one of the conditions that would supplement and make osteoporosis. But for example, that's why they typically say, like, drink your milk, get your calcium. Though milk is not a amazing source of that calcium, but it's good enough. Bone density is often determined by passing low-dose x-rays through the narrow part of the top of the femur, which is your hip. The spine is also typically where they measure this. Part of that is because that's the biggest danger. Those are the most likely to actually have fractures. They tend to support the majority of your weight and have the most stress placed on them. So the bones with high density is going to block more x-rays compared to the bones with less density. As you can see here, more dense, less dense, right? All right, let's talk about measuring density. So anybody heard the story of Eureka? No? All right, so a king wanted the composition of a crown measured, but it's a very complicated structure, and so they couldn't, just measure it with whatever measuring tools they had. And so they were trying to figure out, how in the world can I measure the density of this gold crown with all this ornate workings on it, so I could determine how pure the gold is. And Archimedes, supposedly, but was trying to figure this out, nobody could figure this out, got into a bath. What happens when you get into a bath? Yeah, it overflowed. So the water is displaced. That displacement happens based on the volume of what you put in, right? And so that was the answer. Eureka! And then ran out of the bath, supposedly down the street. Who knows how true that is, but it's a funny story. All right, so this is how you typically calculate the density of most objects, is you would weigh them out on a balance here. Okay? This is not actually a great way to weigh something on a balance, by the way. It shouldn't be precariously tipped over like that, and so it can wobble around. You'd want to actually secure it a little better than that. But you would then put this in a known volume of typically water, that you can use other things as well. This is specifically water with some food coloring in it. Okay? Just to make it easier to look at. And what happens is the volume is then displaced, right? Okay. And that displacement, that is the volume of the object you put in. You do have to make sure all the bubbles get out though. Okay? So it is something you have to tap on the side usually to get to work. All right, so anyways, you take that mass then, straight up the number of grams you got here, and then you take that volume increase and you plug it into the bottom. And that gives you the grams per milliliter, or grams per cc, or grams per centimeter cubed, right? They're all the exact same units. And that's your density. Congratulations. So, John took 2 teaspoons of cough syrup for a cough. If the syrup had a density of 1.2 grams per milliliter, and there's 5 milliliters in 1 teaspoon, what was the mass in grams of the cough syrup? Okay, so go and start working on it. First off, let me point something out. 90% of problems I give you that are math problems are just going to be straight up dimensional analysis. You don't actually have to know anything about anything almost. You can just know dimensional analysis and do them. Okay? So if you just go through and cancel out units until you get what you want, you're going to get like 90% of the problems in this class right. There's surprisingly little you have to actually know about any given problem. Yeah. That's kind of true for the world too, isn't it? Actually, the people that know more about a situation typically have lower success rates than people that know less. Which is so... which really bothers me. On a deep existential level, right? Yeah. Alright. Okay, you guys making good progress? No? Okay. So first off, what do I have? 2 teaspoons. Good. I also have some conversion factors, don't I? Yeah. So the conversion factors I have is 1.2 grams per milliliter and 5 milliliter in 1 teaspoon. What do I need? Grams. Yeah, I want to get in grams at the end of that, don't I? And so I can start off with the 2 teaspoons. This right here goes from teaspoon to milliliters, doesn't it? And that one goes from milliliters to grams. So that's 1, 2, and then this is what I end up with. Okay, let's do it. So I'm going to go from teaspoons to milliliters because I have something that relates those 2 quantities, right? And then what I'm going to do is I'm going to have to go from milliliters to grams because I want grams, right? And this relates those 2 quantities. Okay? That cancels one out and leaves me in the other, doesn't it? Okay. So I'm going to go ahead and set that up. I write out 2 teaspoons. Again, I go ahead and say times my milliliters here, 5 milliliters, divided by my 1 teaspoon. That cancels teaspoons, doesn't it? And will leave me in milliliters. Okay, the next thing I'm going to do is I have milliliters. I want to be in grams. And so I'm going to take my milliliters on bottom. That'll cancel out. And times the grams. Again, that comes from here. Okay. Now, let's go ahead and go backwards and talk a little bit about this, okay? Because I'm noticing a few of you look disturbed. Okay. All right. Now, again, this is what do I have? What do I need? How do I get there, right? Whenever I do any problem. Okay, so what do I have in this problem? 2 teaspoons, exactly. That's my starting point, right? Okay. I also have some conversion factors, don't I? Okay. These are going to help me set up a pathway. These are my checkpoints on the pathway, okay? These are my I turn right at Hardee's. All right? Okay. And so the next thing after what do I have, I want to identify what do I need. I need grams, don't I? Okay. Okay, so I can work from either direction. Who here wants me to try to work backwards from grams? No? Okay. I actually personally find that easier. I know, I'm a nonlinear thinker. But nobody wants to see that?
No, please.
Really? It's actually easier.
But how do you
Can you just show us like one time?
How do you start
And then
the
show
grams?
them.
I will show you one time backwards, okay?
Can you grab a marker and write it like on the whiteboard?
Sure. I can grab a marker and write it on the whiteboard.
Are there markers? Unless there's not a marker, then maybe we're not.
No, there's not. Okay.
Yeah.
Okay, I'm gonna exit out. I'll exit back in.
Would you like a whiteboard marker?
Oh. You took the whiteboard marker.
Why do you
That's really nice.
What?
Go.
Yeah.
Okay. So, folks, again, I always start off with grouping together what do I have, what do I need, how do I get there, okay? I prefer doing them as conversion factors, okay? Now, I have 2 teaspoons, right? And when I'm writing out what do I have, what I need, how do I get there, I typically don't worry about the sig figs and stuff. I'll fix those while I'm writing the problem. Okay, so that's what I have, isn't it? Right? What do I need? Some grams, right? Okay. And so that's my need. Okay. Next thing is I need to figure out how do I get there, right? Or a path. Another way of saying it. If you want to get fancy, you could say it's the Tao. No?
Please don't.
We're going to go Taoism. Okay. Now, the path to get there. Well, I have some stuff that they've given me to help me out, don't I? Okay? And so this can help me out here. This, I should go and list it and the possible things I might use to make a path, right? Just like my ingredients that I could make a bridge or something, or a house, okay? And so I have a 1.2, and I rewrite them all the time like this, because I'm gonna need them like that, okay? Does everybody understand how I can rewrite that like that? Okay, nobody got it lost? Every now and then somebody does. It's an issue. Okay, and then I have this statement right here, which is the 5 milliliters in 1 teaspoon, right? Now that's an equality, isn't it? I can rewrite that as a conversion, can't I? Okay? And so I'm going to take my 5 milliliters, and that is 1 teaspoon. Okay. And so now I have elements that could compose my path. Okay? Now, I want grams here. So what I typically do is I think about my path backwards. So I think about, I want to get there, right? So what has a comparison to grams? That's down here, isn't it? That gives me grams. Okay? And it's in the correct direction right now, because I'm going to end up in grams with whatever I do, won't I? Okay? Now, one of the things I need to point out here is if I had written this like this, is that going to get me in grams at the end of this? No. So please be very careful about that. Very common mistake students make when they're first learning this stuff. Okay? Okay, so this is going to get me into grams, isn't it? But introduces a problem. And that problem is that milliliters right there, isn't it? Do I have something that can get rid of milliliters for me? Yeah, that, right? Okay. And so if I were to multiply those two numbers together right now, I would actually cancel out milliliters, and I'd be left with a conversion of grams to teaspoon, wouldn't I? Okay. Hey, that actually bridges me back to what I have, doesn't it? Because that's teaspoons. Okay. And so now I have a pathway, don't I? All I have to do is just follow that backwards. Okay. And so I'm going to go to teaspoons, railroad track. Teaspoon needs to be on bottom, so it's going to cancel. Okay. Milliliter needs to be on top. And I put in my numbers. Continue my railroad track because I'm in milliliters, not grams yet. And so I put my grams on top because I want to be in those. Milliliters on bottom. And it is the 1.20 versus 1. That's all that is. Did that help? Okay. Okay. The going backwards is faster. Going forwards is slower. If I go from here and I work through that way, I end up with problems of I don't know which one I need on top when it's a very long problem and there's 100 of these. Okay? If you go from the what you need at the end, you always end up with everything flipped the correct way. Mm-hmm. Oh, yes, please. Yeah. Do you want me to give you this back so I don't forget? Do you want me to give you this? I will totally forget, and it will end up on these boards, which apparently is a death sentence. All right. So, did everybody understand that better? Fantastic. Okay, so who's here is going to end up using the backwards method? Maybe?
I feel like I don't have a method. I just write down a bunch of numbers and figure it out.
Okay, that's why I'm giving you the what do I have, what do I need, how do I get there?
Yeah, it's just, I don't know, it doesn't make sense that way in my head.
Try it out, practice. It's something that if you develop, yeah, for these problems right here, you can get away with just randomly writing numbers and figuring it out, and you don't really need to develop a strategy. It's only 2 or 3 conversions, not a big deal. But there are many jobs where you may have to make 50, 100 conversions, okay? And that would be things like figuring out like shipping costs, okay? Or unit prices. And if you start doing that stuff, when you get into the over 10 unit conversions, you really need a methodology and you need to be able to do it step by step by step. Yeah. Or in some of the more complicated conversions at the end of the class, you're going to hit sort of if you do it randomly, I'm not really sure if I'm right or wrong. Yeah. But if you do it methodically, you're always going to be sure. Okay? Okay, we're going to go ahead and do our little plicker. Everybody ready? It's going to be A. Make sure you got A. Double check your things. And okay, you guys are all different directions. Double check if you have A. Hey there. We're answering A on plicker.
The answer is A.
Okay, seriously, look at each other for a second. And there's like a bunch of you with a different direction.
I think that they're just printed under.
Are they?
Yeah, so we can't cheat off each other.
Oh, that's actually cool. Okay. I'm getting paranoid about it because I've been having a lot of people. Did I get everybody? Yep. I've been having like every single plicker that I've done, like 1 or 2 people, even when I tell the answer, get it wrong.
I mean, it is saying that we have it right?
No, it's saying that you did have it right, actually.
Okay.
Yeah. It lights you up as if you answer. Yeah. You should be good. Thank you.
She's so old, just in case.
I mean, it's okay. You could.
She was really upset with that answer.
I think it helps a lot when you wrote it like on the board rather than it being typed on there.
Sure. Sounds good. Yeah, if you need me to rewrite something out, let me know. Many of the problems, I never know which problem is going to actually be the one that's going to catch people. Every semester I've taught this, and I've taught this like 20 times, has been different. Every single time. Every class. So I'm totally fine with rewriting it on the board and working it through.
There was one on the.
Oh, yes, please.
There was one on the lab sheet that like confused me because it had two different like it'd say grams over milliliters, and we had to change both of the units. So it'd be like instead of grams, it'd be micrograms or something, and then the milliliters would change as well. So like I was staring at it for like 10 minutes and I didn't know what to do.
Oh, did you get it?
I think I got it eventually. Which one was that?
If
It
you
was like
want.
one of the last ones in the lab sheet. It was probably 10. Probably.
Feel free to send it on to me. I don't have that lab sheet
Okay.
because I give a different one. But yeah, send it on to me sometime,
Okay.
and I'll make a little video showing how to work it.
Thank you so much.
No problem. Specific gravity. So specific gravity is going to be a relationship between the density of a substance and the density of water. It's basically a shorthand. So what you do is normalize all your densities versus water. Now, conveniently, water has a density that's either very close to or exactly 1. So it's 1 gram per milliliter. So typically what happens is you take all the densities of everything but water and you divide it by basically 1 gram per milliliter. So when you typically see a density, it's already pretty much a specific density, right? Or specific gravities specifically. The specific gravities, the substance with a specific gravity of 1 is going to have the same density of water. It will actually float with the water, and it will bob up and down in the water, just like water will, okay? Depending on it being heated and cooled. If it has a density, a specific gravity that is less than 1, of course, it would float. If it has a specific gravity of greater than 1, it will sink. If it's pretty close to 1, it will mostly sink or mostly float and, yeah, make a bit of a band. Okay. Okay, so this is why specific gravity might be interesting. So this is a hydrometer. It's used to measure the specific gravity of urine. The normal range of specific gravity for urine ranges between 1.003 to 1.030. The specific gravity can decrease with a type 2 diabetes or kidney disease, and so it's a very quick and easy way to have an idea if somebody might have those. Okay, and then you can do longer, more specific testing for them, right? It used to be the primary diagnostic method, actually, and still is used very widely. Okay, and so again, specific gravity may occur with increases may occur if you're dehydrated. So you have much more concentrated urine. You would have already seen that when you go to the bathroom, by the way. Oh, thank you very much. Kidney infections can cause it, and liver disease as well. And so if the person's not dehydrated, then you would want to do more testing. Okay. By the way, did anybody want to hear about or talk about why like boats can float? Why like a metal boat can float? Okay. Okay, so metal obviously has a density that's greater than 1. Significantly greater than 1, right? And so what's happening is the shape of the boat is causing it so its surface area pressing against the water is much greater. You can think of it as if we're mimicking a greater volume. Okay? So if you had made a hollow object like a balloon out of metal, that would also float, right? And so the boat's shape, as long as the water doesn't pour in through the top, is going to float quite nicely, right? Now you can do little tricks, like having like hollow cells within the boat that will help it float as well, okay? And having pumps that move any water that does get into it out, right? Yeah.
What about like those amphibious cars and stuff? They have the same thing going on.
Yep, yep. So typically that's because they're made out of pretty light materials like plastics and stuff. But yeah, it's they're sort of mimicking it having that volume, even though it doesn't necessarily completely sealed volume. Yeah, yeah. Okay. Did that help at all? Okay, cool. Yeah, a lot of the cars that can float for extended periods of time actually have chambers that they can fill with air. Yeah. So there's some pretty cool tricks that they can play. Yeah. Or another thing they can do is just keep the car moving fast enough that its area, a bit like a plane wing on the water. And those ones will sink if they stop. And you can see videos of that. Which are pretty funny,
What
actually.
about like what you said, like when you're swimming and then like you take a deep breath and you float, like you're still denser than the water, right?
If you're floating, no.
Okay.
No, so funny enough, humans actually have a density. It's actually pretty close to the water. Like our fat is actually less dense than water. That would float. And that's actually, if you ever see like that fecal matter or urine that floats on the water, that actually has a lot of fatty bodies in it. That's why that's happening. Okay? And sorry, but so fat actually does float, and we are mostly composed of water in the first place. So our buoyancy, our specific gravity is pretty close to the water. Even a little difference in our lung capacity can change that quite a bit. Now, interestingly enough, our lungs do not actually act like balloons. They are not being filled by the air coming in. What's happening is our lungs are actually being pulled apart by our rib cage. And that's actually pulling air in. Yeah. So this is another specific gravity test we're looking at. And in a clinic or hospital, you'd actually use a dipstick like so. It'll contain chemical pads. And this is going to be used to evaluate the specific gravity of the urine. And so that's how they get away without having to set up like a whole setup like that. Okay? They use the dipsticks right here. You can also incorporate other things onto the dipsticks, like test for acidity, etc. Okay? All right, anybody have any questions about that? Fantastic. Now that I've totally grossed you out. It's all natural stuff. It's okay. All right. So, chapter 3, we're going to be talking about some matter and energy. So, matter is anything that has mass and occupies space. It makes up all the things we use. It can be things like water, wood, plastic bags, everything around us. We can classify matter according to its composition, and so we can have a way of breaking down matter and looking at different compositions. So for example, we can have pure substances. This has a fixed or definite composition. We could have mixtures. This is going to contain two or more different substances. These will be mixed together. They will not be chemically combined. Can anybody tell me a mixture? Most of you have mixtures like sitting right in front of you, or yeah. So soda, coffee, those are all mixtures. Your skin, of course, is a mixture. Your hair is a mixture. The clothing you wear, most of your clothing you wear is probably mixtures as well. Okay. The desk metal, mixture. The desk surface, likely a mixture. Oh, yeah, it's certainly a mixture. I have to check. All right, so again, we can split matter, pure substances, mixtures, okay? So mixtures can then be further split. We can split them into homogeneous and heterogeneous substances, okay? Now, when we look at homogeneous, anybody want me to tell you the Atlantic version across the pond? Sure. Okay. There's heterogeneous and homogeneous. Yeah. That would be the European way of saying it. Homogeneous, heterogeneous, if you don't want to be one of those dang Europeans. Yeah. If you don't want to be a Yankee, then I don't know what you do. 'Cause No idea. So pure substances, these are going to be split between elements and compounds. So elements are the things that are on the periodic table. Okay? So this would be like pure copper. Penny is a terrible example of that. It hasn't been pure copper in basically forever. Like your parents were dead when it was made into not pure copper. So, and it hasn't even been mostly copper for my lifetime. It has very little copper in it. But anyways, there's like pure gold, pure copper. You get the idea, right? Pure oxygen. Actually, pure oxygen and things like that, you would have a much better chance of finding. Gases are typically easier to separate. Compounds. This would be everything from water to the specific like sugars, like glucose, etc. Okay. And again, pure compounds. To be very honest with you, pure substances are very difficult to actually encounter in the real world. Okay? It's something that's more, you need to understand that it exists so you can understand everything else. Okay? Mixtures is basically everything you encounter in the world all the time. Yeah. Okay, so again, the pure substance classified. It's a type of matter with a fixed or definite composition. An element that's composed of one atom is going to be an element. A compound is going to be composed of two or more elements. It's always combined in the same proportions. This is slightly off, and we'll discuss that exceptions later when we talk about the periodic table, okay? But it's a bit of an oversimplification. This right here is an aluminum can. This is one of the few places where you're going to find mostly pure substance, actually. Anybody know what color aluminum is? Yeah, it's a very shiny silver. Do you notice that your aluminums are a little dull looking usually? That's aluminum oxide. That's aluminum rust. If you were to remove that aluminum rust continuously, the aluminum can would actually rust away to nothing in like 15 minutes. Yeah, that's why they don't let mercury on planes. If you spill mercury, it dissolves the aluminum oxide, and it will actually rust a hole in the plane's hull over the course of the flight. They used to actually used to use it for photos. Yeah, it was the flash on photos. That's where it kind of started. And it used to actually be sold like for toys and stuff. And yeah, oh yeah, yeah. Actually, mercury itself is not very poisonous. It's actually very difficult to harm yourself with mercury. Like you can give it to little kids and they can swallow it and it's not a problem. The problem is when you get mercury alkylates. Those are poisonous.
What about like mercury in hats and stuff?
Mercury in what?
Like hats?
Oh, yes. You heard the Mad Hatter?
Yeah.
Yeah. So everybody knows Alice in Wonderland, right? Which was actually a commentary on Victorian age England, right? So the Mad Hatter is actually a depiction of somebody that has mercury poison. So he was poisoned with mercury because back in the Victorian age, to make those felt hats, they'd have to use a mercury compound to do it. And so all of his quirks in that novel are actual symptoms of mercury poisoning. So like you're very easy to anger, you tend to be a bit clumsy, shaky, not be able to modulate your volume and expressions well, because you end up with nerve damage. Anybody ever heard of artisanal gold, by the way? So that's the modern day thing that happens where you get mercury poisoning. What artisanal gold really is a gold mine where they don't have smelting machines. And so somebody sits over a fire, takes the ore, puts mercury with it, that combines with the gold in the ore, brings it out, and then they literally smelt it in a little pan over a fire. That's artesian gold. If you ever see it, it's brutally bad and usually has a huge history with slavery and genocide, and it's a very, 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 very bad thing. Okay?
Do you get mercury poisoning by like consuming it, or is it like a respiratory? Like, how do you even?
Typically, you would get it through respiratory. So you would have mercury go onto something that's hot enough to boil it, and then the mercury would get in your lungs, and then you can't get rid of the stuff in your lungs. So it would slowly alkylate and go into your blood. The other way that happens is there's certain fish and plankton and stuff that will uptake mercury, and so they will alkylate it, and then that goes into the environment. And that's why mercury is like banned everywhere and getting rid of. It's that plants have a tendency to uptake it. It gets concentrated as you go up to different food spots. And once you get to a certain concentration, there's a very good chance you're going to get some alkylated form. And that gets more and more concentrated, and then we start getting usually birth defects are the problem. The nerve damage to the babies, not the. Yep. Yep. Yeah. That's why you want to avoid fish, because mercury tends to go into the oceans the worst. Yeah. Elements. These are going to be a pure substance that contains only one type of material. So it'll be if you can divide something down until it starts losing its properties, this is the last step where it's going to not be having lost its properties. So it's still recognizably copper. Okay? Still recognizably lead, aluminum. All right? And these are the things you would see on the periodic table. You can get pretty pure elements, but you can never actually get fully pure elements. That's almost impossible. Compounds. So these are most of what you usually encounter in your daily lives. I'm going to be honest, though I say that, aluminum actually is quite pure because it's done through electrochemistry, and they have to use tremendous power to generate, by the way. The only countries that can do it are countries with a bunch of nuclear plants. Yeah. So it's actually like miraculous. Anybody want to know what the silverware that you would dine kings and queens on would be composed of if you were Napoleon? Nope. Nope. So if it's just a minor person, you don't care if you offend them, you might serve them on gold. If it's somebody that you really don't care and you want to make a statement, you'll serve them on silver. So that's saying you're not important enough for me to bring out the good silverware. If you want to really wow them and you're Napoleon, you feed them on aluminum. Because literally, Napoleon owned the majority of aluminum on the planet in his silverware set. It was a power statement. I know, right? Now you go in Walmart. Camping, aluminum, silverware. Dine like Napoleon. That should be the sad. So hydrogen peroxide, table salts, sugar, water, these are all compounds, okay? Table salt, this is going to be a compound that contains the elements sodium and chloride. Anybody ever seen a molecule with their eyes? No? Can you guys see my hair? Can you see your hairs? Maybe. Those are molecules. Yeah. They're just very, very long molecules. Like everything runs you molecules. Table salt would also be considered a singular molecule. Okay? You wouldn't be able to find the beginning or end of it. Yeah. And so table salt, when you're looking at these crystals, that's actually the shape they lay out when they bind together. Okay? Which is kind of cool. This is sodium metal, by the way. That's chlorine gas. Those are the components of table salt. Ooh, Okay. All right, so mixtures. It's going to be a type of matter that consists of two or more substances that are going to be physically mixed. They will not be chemically combined, though, which is one of the reasons you can separate out mixtures much, much easier. Okay? Now, the two or more substances in different proportions that can be separated by physical methods. That's another definition for mixture. Spaghetti would be a good example of a mixture because you can separate the water in the spaghetti quite well, right? Literally through well, straining is what it's called, but filtration would be the same sort of methodology, right? Like a coffee filter. This would actually be a laboratory separation of mixtures, and here we actually see filter paper. This is very, very similar to how you would do like a coffee filter, right? Or a tea bag, okay? Very similar methodology. There's little gaps in the paper, the water can get through, the particles in here cannot, right? And there we go. This right here is actually chromatography. This is a chromatography paper. And anybody ever dipped like a paper towel in water and seen it go up? Same thing, okay? Typically not using water here. Typically something like acetone or it might be a hexane or something. But you have a substance, you dotted it right here, and what happens is part of that substance travels much faster in the solvent you're using, part of it travels slower. And so over time, you actually get the different components separating. You can actually do this yourself at home using paper towels and like that Expo marker. Yeah. And what you would actually find out is most colors that you're given, like especially the blacks, are really just all the other colors dumped together in a vat and handed to you. Yeah. So you'd see lots of stuff. Okay, so in a homogeneous mixture, you can't see the difference. All right, that's the big hint. So your composition is going to be uniform throughout the sample. The different parts of the mixture are not going to be visible. The metal down here is probably a homogeneous mixture. The desktops are not homogeneous because they did patterning in them. The tiles up on top are not homogeneous, right? How about air around you? Can you see the difference between the air parts? No, so that's a homogeneous mixture as well. The air you're breathing. Okay. Okay, a lot of your drinks are probably homogeneous mixtures as well, because you can't see the individual parts. If you have ice in them, it might be a heterogeneous mixture because of the ice. All right. So when we're talking about like scuba breathing mixtures, the breathing mixtures for scuba are going to be homogeneous mixtures. Overall, gases tend to be homogeneous mixtures. Nitrox, that's oxygen and nitrogen gases mixed together. Heliox, which is oxygen and helium gases mixed together, and that's super expensive nowadays because helium's really been going up in price. Trimix, which is oxygen, helium, and nitrogen gases mixed together. And the helium allows you to have more oxygen while it's still not being flammable and having the bad things where you have pure oxygen. Okay? In case you're wondering. Nitrogen and oxygen mixture is what we're breathing right now. Okay? That's the primary elements in the air we're breathing. Heterogeneous mixtures. This would be an example of a heterogeneous mixture. Composition is going to vary from one part of the mixture to the other. The different parts in the mixture are going to be visible. So the ice cubes in your drink, that's a heterogeneous mixture. The desktop, because you can see different parts of it, is going to be a heterogeneous mixture. The tiles up there are heterogeneous mixtures. You can actually see different parts of them, right? Our faces are heterogeneous mixtures because you can see different parts, right? Glands and hair and etc., right? Okay. Okay. So let's identify each of the following as a pure substance or a mixture. Pasta and tomato sauce. Mixture. Aluminum foil. Pure substance. Yeah. We'll go with that. Helium. Pure, yeah. Air. Mixture. Perfect. Yeah. So, technically speaking, the helium foil has a very thin skin on it. So, but even that would be two pure substances. We're definitely not trying to make a mixture. So identify each of the following as homogeneous or heterogeneous mixtures. Hot fudge sundae. Heterogeneous. Baby shampoo. Homogeneous. Most baby shampoos, right? I guess you could probably find something that you could go. Sugar water. Homogeneous, because you can't see the differences. Yeah. Peach pie. Heterogeneous. Yeah. If it would be homogeneous, that would be disgusting. It would be really sad. Now we need to talk about the phases. Yeah. I'm only going to give you 3 phases. I know. Yes. Yes. The suffering. Okay. If anybody wants to ask me about the other phases, you can, but that'll be outside the context of this course. Okay. Solids. These have a definite shape and a definite volume. Anybody identify a solid for me? The desk. Yeah. Does it flow? Is it changing its shape? Nope. Does it stay the same volume or does it expand to fill the room? Yeah. Yep. So solid. So particles are going to be held closely together. These are by strong attractive forces. This is in fact what makes it be a solid, because it's being held so tightly together it can't move around easy, right? Yeah. So the particles are going to be arranged in a rigid pattern. This can only vibrate slowly in your fixed positions. Basically, all matter is all vibrating all the time. Okay? All the particles are bouncing around. But in a solid, they're kind of trapped in place by the connections between them. Right? Your shirts are actually a great example of a solid, and you can really kind of envision them bouncing around and moving all the time, but they don't go very far, right? Because they're solids. Liquids, these are going to have a definite volume. They will not have a definite shape though, right? They will fill and change shape to conform to the container, as you can see from many bottles of liquid in front of you. Okay? Oh, is it time? All right. You will have a wonderful day. I will see you next time. If you have any questions,